All right. Hi. So I hope you are having an exciting time here. No? Yes? I'm sure you are having. So please don't take it as a talk, more like a discussion. This is just some background to talk about. Okay, so stop me anytime. I want to hear you more than I want to hear myself. Okay, which is not a good thing, by the way, hearing yourself all the time. So please feel free to stop me anytime. Small doubt, I speak fast, I didn't pronounce a word correctly, I'll try to improve. So this, I have titled it as Laser 101, just for the sake of it. I mean, it should have been Introduction to Lasers or whatever. So what Harishji put as the title was what lasers do. So I thought first let's just talk about what laser is, which probably already been introduced, isn't it? Some notions of laser you are aware of. I don't know whether it has been formally introduced, I have no idea. During the...
Did you have this laser in your part?
Then I can talk only about some other things. I see. Okay, in the lab. So I'm sure you have many more questions after doing the experiment. Okay, so we'll be, so we will talk about it. So this is some kind of a pictorial introduction to lasers. Okay, people do spend a course trying to learn it right, doing the mathematics right. See, we can always talk about generalized things, but physics is such a science that you cannot afford to dislike mathematics. You're right, because nature speaks that language. Whether you like it or not, you will be stuck with it. So as well like it, right? So that is one very important thing. How much ever you might not like it, you need to personally start liking mathematics, because that's a language that's a language of nature. All right. So this is supposed to be the year of light, isn't it? No, the previous one. It was declared the year of light, and of course this slide I had put it last time, but I think it's important to understand that light has really transformed our daily life. Okay, so for example, a more important transformation would have been maybe, I don't know, Faraday's law, right? You know about Faraday? So when Faraday discovered his law of induction, right? Obviously it was something very strange. Magnetism and electricity were put together, all that is okay, but then there was something very strange that you could create electricity out of moving magnets, right? So he was asked, what is the big application of this thing? What can you do with it? And he gave a very fantastic answer. The answer was that, what is the use of a newborn child? Right? So you don't know what's going to happen. So that is precisely what light has done to us. I mean, so the light-based technologies came in only in 1960s or so. It's not that people didn't know that it can be used. People knew it can be used, but then we didn't have a good tool to do it right and do it well. So only after the invention of lasers that the whole thing just flourished. It just turned out into be something. So I think some of these lines are very important. Light plays a vital role in our daily lives. Cross-cutting discipline of science, and absolutely everywhere you go now there is light-based technologies, right? From internet to name the thing. Yeah. All right. So these are some people who, according to me, were at the beginning of this story, right? So the very, very beginning is, of course, Albert Einstein, without his notion of photon. I mean, this business of quantization, business of understanding what light is, none of this would have happened. Most importantly, he put in this extra idea of stimulated emission. Okay, so people thought that if you knew, okay, atoms are quantized, that itself is a leap of thought, right? Atoms are quantized, you put in the excited state, yeah, you will emit. But then he came up with a distinctly different process, intrinsically different, which is that business of stimulated emission. And that's precisely the starting point of all that people did. So Theodor Neumann, he invented the first laser. No, what is the other one? First was what? There's something called a maser. You recall that? Microwave. I'm sure you heard of this business. See, what happens is lasers have, okay, optical light has small wavelength, isn't it? What's the size of wavelength of light? Typical visible light? 400 to 600 nanometers, right? So there's 10 to the power minus 7 kinds. Whereas for microwave oven, what is the wavelength? It can be in, any idea? We should know, right? Because microwave we use all the time. 10 to the power minus 2 centimeters? No? Millimeters? Okay, centimeter, millimeter, that's good enough. So what happens is now you want to confine this light into cavities, which I will talk about, which are comparable to the wavelength of light. That helps us do something. That allows us to choose wavelength correctly. Okay? That's very important idea. And by the way, choosing this wavelength correctly got 3 people Nobel Prize here. Okay? So it is this idea of choosing the wavelength correctly. So you could do it in systems which are larger wavelength. You can make larger cavities, easy to understand. When you go to smaller and smaller scale, it's more difficult. That's why maser came first, laser came later. Then Kastler did this work prior to the laser, 1940s or so, and maybe he got the Nobel Prize in 1950. This was to do with how to manipulate atoms. So atoms, put in electrons on the excited state, but you want the electrons to go to a particular state. Because when you put the excitation, it will go everywhere. If they are energetic levels, all of them will share the electrons equally. But you want them to go to a particular set of states. Okay? This was something which Kastler invented called optical pumping. Okay? This got to do with some angular momentum conservation between how the atoms go up, and then he prepared it just right to populate a particular level. This is what is, if you recall the word like population inversion, which is familiar with lasers, it arises, the population inversion achieved by ideas introduced by Kastler. Then Shallow and Towns were the first ones to, actually Charles Towns was responsible for even identifying what we should use as a laser. Okay? So there's an active material, something called ruby laser was the first one that was made. That identification and that working largely was done by him. He also calculated the line shape. Okay? I'll come to these words. These are all words which I am emphasizing, line shape and all that. So Towns and Shallow did that. Independently, Bashov and Prokhorov in Russia, they independently invented, in a sense, this business of choosing a wavelength for a laser. So just like these guys did. So I will come to this choice of a wavelength just down the talk, but remember that these are the contributions. And this is Bennett and Javan, they made the first gas laser. In the sense that people thought that there was one laser, we are done with it. Then the moment you made something else, you realize that, oh, you could make with almost anything. So almost anything can be made to laze. I remember during my PhD days, somebody had made a piece of bread laze. It won't be an efficient laser, but then you can make it laze, as in give coherent radiation, right? So this idea that you could make it with almost anything, and there's a huge family of lasers that people know, there are all kinds of lasers at all kinds of wavelengths. All that has come because of these initial ideas. So these I call them as the architects of laser. So this is the plan of the talk. Let's not worry too much about it, but this is something that you might appreciate or like. So these are extreme lasers till date. We have to understand why we are having so much fun, because if we don't know what the extremes they are getting, what's the point? So for example, the military loves to make more and more powerful lasers. They can shoot down somebody. Apart from that, there are other applications which are better, okay, saner. So these are some of the things which might be a little old. Maybe this is about a year or two old, but things haven't changed dramatically since. But then this is a list that is quite amazing in terms of numbers. Okay, so my usual interactive class would be, what do you think are the characteristics of lasers, right? So you will say highest power, you will say monochromatic, you will say this, that. So we can take all these ideas and ask what is the best people have done to that. We are saying highest power, how much highest power? How much average highest power, continuous? How much pulsed highest power? You can ask such questions, right? And these are essentially a list of these extreme situations that people have achieved. All right? So let's look at this more carefully. So highest energy laser pulse. Pulse implies what? So you have seen these laser pointers, you just put it on, light is there everywhere. So what I do now is, in time it is spread out everywhere. In time I shrink it and make it into a pulse. Put all that energy which was spread out in time into a very small duration. Okay? And just give that pulse of light, and that of course gives me much larger powers than what would be there in a continuous wave or a spread out continuous laser, right? So the highest pulse powers, so you can get a megajoule, mega is 10 to the power of 6 joules in 1 nanosecond. Okay, about a nanosecond you can get a megajoule. You understand what that means? So 10 to the power of 6, so if you look at power, this is 10 to the power of minus 9, right? So one is talking of really, I mean, huge power. Not easy to make. What they have is 192 lasers. What they are trying to do with this is actually create fusion. You know what is fusion? People want to, just like sun produces energy with hydrogen create helium, and that excess energy is what sun produces, and all of these are safe to us, right? We don't take uranium-235, break it up, that is not so clean technology. We want to do fusion. So we want to simulate and get conditions that are similar to what is there in cores of stars. You know, that's where fusion happens on a regular basis. So we want to create that situation. So here what they have is a less than a centimeter size cube or a pellet, in which lasers, 192 lasers, are just timed right to produce this huge pulse of light which compresses this pellet from all directions. Hopefully when you provide sufficient pressure, the radiation pressure which is coming in, they will combine and create. So right, so that is what is the highest energy, which comes out to be a very, very large number, right? So it's 10 to the power of 15 or so in terms of wattage. Shortest laser pulse, right? The shortest laser pulse, that is, you are taking this pulse which is continuous, say CW laser, which is there all the time, you are shrinking it to what time scale, or the shortest time scale you can shrink it to is 10 to the power minus 15 of a second. Okay, so remember that when you calculate for, let's say, 500 nanometers, 600 nanometers, what is the linear frequency? How much would you get? 10 to the power 14? You understand, right? What I am asking is C is equal to nu lambda, right? I am asking about when you are having lambda, which is about 400 nanometers, so 10 to the power minus 7 there, 10 to the power of 8 here, and you are asking what the nu is. So that is the oscillation in time. So basically you have about a femtosecond, or maybe more than that, tens of femtosecond. So you see that if you think of the light wave as a sine wave, this period itself takes about 10 to the power 14 of a second. If I want to make a pulse which is shorter than this, the electric field doesn't even go through one cycle. You understand that? The electric field is just gone like that. Barely a cycle has happened and you have shut off the light. So it is on, and so this is off. It is just that much electric field, right? So it is really, really small. We are not even talking of this notion of a wavelength itself, goes away, right? Where is the repetition? So it's that short. So the shortest laser pulses you can get through this. The highest instantaneous power, okay, Abhi, it's 10 to the power of, what is a petawatt? 10 10 to the power of 15. Okay, that's the kind of. So you can do better than this. This is just in a nanosecond, but you can bring it down to 440 femtoseconds. Compress it even more, you can get a little more. So that's typical. Highest average power is more than a megawatt of continuous power. Okay, that is a continuous light megawatt of power. It's you require much lower power to melt steel, by the way, to cut. Okay, so that's of course I have stated this as the deadliest laser, but we don't want to talk about it. But basically, these are US Air Force loves to shoot down ballistic missiles. They want to do that stuff with. Let's not worry about all that. We don't talk about such. Longest laser, okay, in terms of size, 1.3 kilometers long. Ridiculous, right? 1.3 kilometers. एक mirror उधर है, एक mirror उधर है, and you are aligning it. You know how difficult it is to align in your lab itself across the table, and you are doing this across. It's line, yeah. Yeah, yeah.
When we study about measurement of speed of light by piezo and
Yes,
that,
yes, yeah.
they said that the mirrors were 8 kilometers apart.
Absolutely.
How did they arrive?
Absolutely. That's amazing. Physio's experiment in Paris, on the streets of Paris, and he would try to, he of course has to do it in the night with a wheel where there's a pulse of light. I mean, I just can't imagine how they did it. Imagine an old man with, beard, walking or aligning something 8 kilometers later. It's absolutely amazing. Yeah. And those measurements are so close. I mean, in terms of reliability, just absolutely amazing. Yeah. I think that's an experiment that you have to really keep in mind. To do that, with a wheel and pulse of light coming and wheel rotating fast enough so that the next one goes through, so that that angular speed and this is related. It's a very, very important and very nice experiment. Okay, so longest laser is about 1.3 kilometer long. This is actually a free electron laser. So it is not even, okay, let me not get to this. What you have is basically electrons which are wiggling around. So you know that if there are charged particles and if they accelerate, they radiate. Simply charged particle just is there, it doesn't radiate. If you accelerate it, then it radiates. So what you do is, acceleration can be, you give me a speed, but I change your direction. So periodically there are these magnets which are north-south, just the reverse. One is north-south, the other one is south-north. So you see that the magnetic field is changing. So these guys will now wiggle around, make circles around. So they will wiggle around this wiggler magnets, and they can be as big as that. Right? The shortest laser, like you have a longest laser, you can have a shortest laser in 1 micron size, micrometer, right? You don't even expect. Micron is, so it is something called vertical cavity surface emitting VCSEL, vertical cavity surface emitting laser diodes. So you have just the surface in which the light gets amplified, and all that stuff for a laser happens in this 10 to the power -6 of a meter. Very, very important tool for lots of lab experiments. Then these are very interesting ideas that one must understand. What is the shortest length measurement that one can make? Right? You have got a laser, you want to make it accurately, you want to measure the shortest length that you can measure very, very accurately. So interferometrically, you can measure 10 to the power of -18 of a meter. Terrible, right? 10 to the power of 15, you have got 10 to the power -7 meters is the wavelength. Oh, I say wavelength by 2. But interferometrically you are able to measure 6, 7, 8 orders of magnitude below that. It's absolutely amazing. And part of the technology is what detected the gravitational waves recently, right? So as you are studying, textbooks have changed. Gravitational wave, nobody knew they existed, but now they know they exist. And what is the kind of, one can measure length scales which are shorter. So 10 to the power minus 15 is already the size of the nucleus of an atom. And you are talking about 10 to the power minus 18, 1,000th smaller than that length scale you can measure. So that's amazing. And the shortest time that you can measure. Now you say 10 to the power minus 15, but that's just one cycle, right? No, you can actually do 1,000 times better than that. And these are what are called as attosecond lasers. So this 12 attosecond might be, it keeps improving on a yearly basis, so that might be wrong. But idea is 10 to the power of minus 18th of a second time one can measure accurately. Almost everything is frozen in the time scale, please remember that. That's what people are trying to do. 10 to the power minus 15, laser itself is, right, 10 to the power minus 15 oscillation. Chemical reactions, 10 to the power minus 15 is sufficiently fast. But then almost every reaction is frozen at 10 to the power minus 18th of a scale. You want to just see the reaction as it happens, stroboscopically. You know? So that's the kind of time scales that one can. So these are the most exciting times in terms of what one can reliably, scientifically achieve. Okay? So that is the excitement of being or doing stuff with laser. Okay? So I'm trying to sell it. Let me put it that way. If you can pursue optics, that's one area where you can actually see what you write. You write some equations, something, get something. You can actually go and see it in the lab. No other area allows you that little pleasure. Okay? So if you are thinking about what it is, then all right. So small quick introduction pictorially, this is what one imagines light to be. There is electric and magnetic fields, transverse to the direction of propagation. But actually this is a very terrible story. When you are very kid, one is told that light travels in straight line, ray diagram, ray, and then you slightly get better. No, actually it's a wave, let's not say it's a, and then we come back, by the way, then we'll say, no, actually it's just a photon. It's neither this nor that. It's not. So it's a messy business. But it is messy because it is what it is. So if you make an experiment with light and ask it to show, like Anand would have done, maybe ask it to show its wave-like character, it will show it. But he has a very nice CCD which can measure particle-like character in the same experiment, which is showing wave-like character. It will show it. So the problem is with us that we want to bracket it as wave-like or particle-like, but light doesn't care a damn. It is both wave-like and particle-like at the same time, right? So this is the view that one has in the mind, what light is. So remember that the ray picture is in the limit that the wavelength is going to 0. This wavelength business is not there. Ray is just the direction in which it propagates. So that's a very classical picture. You know, you can do this ray business across a prism. You have done all that 1 by u plus 1 by v is 1 by f and all that. All that is ray picture is very, very sufficient. And when you come to this, it's a little more, you have to now worry about what is the distribution of light within the ray. Then you are asking some more detailed questions. Then you start worrying about this wave-like picture. Okay? Then you make it very, very low light levels. Then you ask some questions, and then you become like photon-like picture. So what is light is a messy answer depending on what you ask, in what context, right? So of course this is an electromagnetic spectrum. We are only interested in the light part of it, but there is nothing philosophically different from any. I'm sure this is something I picked up from internet. So just look at this picture very, very carefully. The sizes of the wavelengths go from as large as buildings and football fields to all the way to the size of the nucleus. There is a variation of possibilities in terms of wavelengths that can happen. That's the whole electromagnetic spectrum. And we are in this very, very narrow visible business where, you know, the only things comparable is this small protozoa, bacteria. That's the kind of size one is talking about. But then it can be from anywhere to anywhere. So see microwave, 10 to the power minus 2. That's the kind of wavelength that one is talking about. And then frequency can all the way something which is of few kilohertz, right? That is 1000 times in a second, all the way 10 to the power 15 times in a second, right? Please understand there are some lasers which I'll talk about, something called something called bandwidth of the laser, right? Somebody says that the wavelength is 400 nanometers, right? You can ask, did you mean 400 or 401? No, 401.23. Now you're getting serious, right? So when you keep asking what exactly do you mean by, so eventually he has to give you a number and some kind of a plus minus, right? That is what we call as a bandwidth. What is the accuracy with which? Just like I'm talking about in wavelength, you can ask what is the accuracy in time. 10 to the power 15 hertz, you mean 10 to the power, that is in a second I will count 10 to the power of 15 oscillations or 10 to the power 15 plus 1 oscillation. Does it make sense? That is the kind of accuracy that people can get. Few hertz of accuracy across 10 to the power 14 hertz. Really monochromatic. We seriously mean what we mean by a unique frequency, right? So this is a important thing which you can certainly pick up from the web. And okay, so what I'm going to display is probably what you would have told me. Basically ask, what is a laser? It is supposed to be monochromatic. If you guys can't see, you can come and sit that side if this is becoming tough to see. So laser is supposed to be monochromatic, right? Monochromatic means single frequency. Interestingly, so that single frequency business is this delta nu. That is, if I plot some kind of a power as a function of frequency, then for a laser I will get something like that, right? At a particular frequency. So this is my nu, and this is the width narrowness. So this what I'm calling it as delta nu over nu, right? Obviously, if delta nu is very small, this ratio is very small. By the way, for sunlight, you know the Blackbody radiation formula, isn't it? P of nu over nu will go something like that, no? Bell-shaped curve. Heard of it? Blackbody radiation. Yes, you have read it. If you look at this width and this frequency, they are same order. 10 to the power of 15 hertz, this width is also 10 to the power of 15 hertz. So delta nu or nu for sunlight is actually 1. Whereas imagine narrowing this down to a single line, it can be as little as 10 to the power minus 13. Okay? That is 10 divided by 10 to the power of minus, right? 10 divided by 10 to the power 14. So that will give you, in so many hertz, you are accurate to 10 hertz, right? That's the kind of accuracy you can get. That's one characteristic of laser. It's a very narrow band. Okay? All the energy is focused into one wavelength. What about directionality? It is extremely directional. Right? Sunlight will give you any light, this will give you light all over, in all 4 pi directions. Whereas laser light gives you something which is very directed. It is not really parallel, by the way. It's nothing can ever be parallel. That is because of something that we have to, something called diffraction limitation is there. Anything which is finite will actually expand. Okay, that's a limitation that is there intrinsically. But this can be extremely narrow cone. People have sent light to the moon, got it reflected back, and seen that same light and measured. Right? So it is really, really narrow, and that solid angle can be 10 to the power minus 8 of a sterdian. Okay? If you want to think what a sterdian is, it's like square of radian. Okay? So if I look at angle, it is 10 to the power minus 4. 10 to the power minus 4 in this direction, 10 to the power minus 4 in that direction. That's a solid angle. So one can think of it as, so that's a kind of narrow directional beam that you can get. So you see that lot of power packed within, but you want large intensity, right? You want power in it. So one can think of power per unit area, right? That is what is watts. So I am putting up a quantity called spectral brightness, which captures all of this into one number. It's something nice to compare. So what is it? It's a power per unit area, per solid angle, per frequency bandwidth. Okay? How much you are shrinking into one narrow place. And for the sun, if you calculate this, it's about 10 to the power minus 12 watts. For helium neon laser, which is what you have seen in the lab and used yesterday, that is 25, is 10 to the power of 12 or 13 orders of magnitude higher. That is why it is not a good idea to put it in your eye. Looking at the sun is different business. Looking into a laser is totally different business. Okay? So it's a dangerous device. Never look at a laser in the eye, and that is precisely because of this power being compressed in an extremely small solid angle, extremely small frequency range. So what it does optically to whatever is there inside the eye is totally different. It's a different ball game completely. Whereas there's a normal laser in any lab, 100, 10 to the power 4 megawatt laser, large labs, that is like 10 to the power 8. So that is like 20 orders of magnitude larger. Okay, you can deal with such numbers only with resistance in the lab. Resistance has this 20 order of magnitude variation. But this is light, spectral radiance can have this variation very much within this thing. So it is what we want to call a laser. Right? Now, just putting these extra, so what I can do is this, I can take sunlight, right? And I belong to a very rich family, then I can buy a very large parabolic mirror, very large, collect a lot of light, focus it down to a very small spot, right? I can use lenses and this and that, narrow it and make it a parallel beam. I can do that, right? Focus it down to a focal point and then put a lens and make it a parallel beam. That will be like laser light. But you say, oh no, it's sunlight, it's got all the colors in it, fine. I'll put a filter, it will cut down my light, but still I have collected a lot of light. As I am getting richer and richer, I am collecting more and more light. So in principle, I can generate exactly the same brightness which I mentioned earlier. Lot of light contained in a small spectrum, just using sunlight, right? And pick up a narrow frequency range, and all that you can do and actually generate same light. Then you ask, oh, what is the difference between laser light and this light? It has got all the characteristics. It has got the power, it has got the frequency selection, it has got a solid angle, concentrated, name the thing, but it is made out of sunlight. Intrinsically, it is born out of a different process called spontaneous emission, whereas there is something different about laser, right? And that difference is what we call as coherence. Okay? What do you mean by coherence? So again, we are again thinking of waves. We are thinking of variation of waves in space as well as in time. I tried to describe. Remember that different colors have been drawn for different frequencies. Different frequencies implies different color. So you see that incoherent light is basically a bunch of this. If I am sitting at one point, I cannot predict what the phase will be at another point. That's incoherent light. I have no idea. There's no correlation between one spot and another space or time separated spot. Whereas a coherent light, if I am at one point, I can precisely predict what is going to be the light phase, amplitude and what all that at another point. Okay, that is what a coherent light is. Right, so this is, so we talk about two kinds of coherence. There is something called spatial and temporal coherence. Right? So I have, so you can clearly see there's a light beam where this is in time, right? In time the wavelength is kind of changing. But in space they are changing together. This guy goes up, this guy goes up, this guy goes up. So you see that this is spatially coherent, but it is not coherent in time. This is the kind of light that you get out of stars. Starlight is spatially coherent, but it is not temporally, because it has same frequency as sunlight. So you will learn later something called Michelson stellar interferometer. Have you heard of it? No Not yet, right? Yeah. So you will worry about that. And so basically this coherence, this distance depends on the angular size of the star. Sunlight, sun, what is the angular size of the sun from our side? From Earth? How much is the angular size of the sun? Any idea? 3 or 4 degree? Actually much smaller than that. Much smaller than that. So you see that if you put in the size of the sun, I am not telling you the answer, surely. Because if I tell you, you will forget it as quickly as I have said it. So when you find it for yourself, you go home, Wikipedia it, and find out what is the angular size of this. Same star, there is something called Alpha Orionis. This is a star which is the closest, Betelgeuse, right? On the Orion constellation, the shoulder which is bright and yellow. That's the nearest star other than the sun. That guy's light, when it comes here, it is 6 meters, it is coherent. Whereas sunlight, when it comes here, it is coherent only to about 0.2 millimeter. That's the size of coherence. That has all got to do with the amount of coherence is inversely proportional to the angular size of the star. Okay, so please check that out and figure out what is the angular size of the sun. But then narrower the angular size, greater is coherence. So by the way, this is how Michelson first measured the size of stars. People didn't know the size of star. So he found out, oh yeah, this gives me some kind of fringes. As I go further and further away, fringes disappear. So that disappearing of the fringes, that distance d where the fringes disappear, is a measure of how much coherent, will quickly give me what is the angular size of the star. And if I know the distance through some other independent measurement, I can tell you what the size is. So that's how the first sizes of stars were actually measured. Similarly, there is something called temporal coherence. This is a coherence in time. So you see that this is a particular wavelength. Time means they are nicely periodic. If it's nicely periodic, I can predict who is going to come later, right? That's what is temporal coherence. So you see that these are, of course in space I am not able to predict, this guy is middle, so this is somewhere else, this is somewhere else. So, but you see that in time I can actually predict, and that temporal thing depends on the frequency content of the light. Okay, narrower the frequency, better is going to be the coherence, right? So more time in coherence. So this narrowness is what, so it is these two aspects put together that actually generate something called a coherent light. And the other important thing which but you say that these are precise that we already spoke about, right? Delta nu is same thing like bandwidth, theta is same like angular spread directionality, already spoken. So this cannot be, so the actual difference between the laser light and the sunlight is because of, I'll probably come back to that, is because of something called photon statistics. Okay, so it's only a higher order correlation that distinguishes laser from other classical sources, but that is just a little advanced topic, but we'll not worry about it. But whole idea is you're asking, let me just tell you the essential idea. So you're asking that, okay, one photon has come, now you're asking when does the second photon come. So for a laser, I won't be able to predict when the second photon comes, it's precisely random, completely random. Sunlight, these guys will come in bunches. The photon comes, there's a very large chance that the second photon is coming with it. There is something called bunching that can happen for thermal light, and which is this statistics is what one has to measure to distinguish between whether it's sunlight or it is going to be something which is a coherent source like a laser. All right. So again, this is just a cartoon which I'm sure Anand has talked about. There is a wave-like business, there is a particle-like, which both of them show the same thing. You have probably seen the movie in his lab, where he has got, where it integrates it just right to get few photons at a time. Okay, right. So this is where the beginning is. All this was storytelling. So there are these 4 elements which are common to all lasers. Okay, I'm just trying to give you essential ideas. So what does laser stand for? That you know, light amplification by stimulated emission of radiation. In that sense it is laser. Of course this name is a slight misnomer. At the end of the talk you will know what I would like to call it, but for obvious reasons people don't call it. But whole idea is this: you have something called an active medium, okay, and this active medium, it could be, so it's a very, by the way, laser, the area is very, very wide, in the sense that you require expertise from aerospace engineering, from chemical engineering, from electrical engineering, name the engineering, all these guys have to contribute to make a proper laser, because there are just too many aspects. So this thing can be atoms, gas, solids, liquids, jets of gas coming out, supersonic jets, name the thing. Active medium could be anything. Okay, so all variety exists. Then what you do is you give a feedback to this light. So just because light comes in doesn't mean you just leave it. You ask it to bounce back and forth. Why? Because you want to generate more and more photons using something called stimulated emission. So one guy goes, bounces, becomes 2, becomes 3, and so on and so forth. This is a cartoon. You'll have many, many atoms and many, many multiplications that happen. Stimulated emission happens at every step. So you want to give it a positive feedback. So making of these lasers, stability, all that becomes a very, very important aspect. So this is what gives you some selectivity, okay, in terms of frequency also. Of course, none of this comes for free. Imagine putting something, mirrors, and then you are getting a lot of laser out. Somebody has to put energy, which you will extract out as coherent energy. So you require some excitation mechanism. Excitation mechanisms are all kinds, all the way from what happens in a tube light, you know, which is some kind of a discharge setup. Electrons are putting in energy into the atoms. It can be other lasers putting in, it can be flash lamps, it can be chemical, it can be some chemistry driven in terms of, it can be some reactions in which some byproducts midway are used. So all kinds of stuff are used for, so chemical, optical, electrical, all kinds of energy is used as a excitation mechanism to pump this energy and extract it out as laser. So these are the 3 elements. The 4th element is, just because you put in a lot of light, that's not sufficient. You need to extract it carefully, right? If you extract it, if you extract too much, not enough feedback. If you extract too little, this guy gets burnt up, because there's too much energy contained within it. So you have to extract it just right. That requires some detail. So you require some partially transmitting mirror as a way to extract. Okay, so when I'm talking about transmittivity, I'm talking about 99.996 kind of reflectivity and 99.87. So it's really, really small light that you extract. Most of the light is actually inside providing. So one has to do that optimally. This itself. So these are the elements that are there in all lasers. Okay, the detail of each one of them will change differently. Okay, so this is the simple processes. You have absorption that happens, you have spontaneous emission that happens, but you want what you want is photon comes in, electron in the excited state, and 2 of them come out exactly identical. And in principle, these guys, you cannot make out which is which, quantum mechanically. I mean quantum mechanically. That is, you can never make out which was a stimulating one, which was the exactly identical particles. So you want this process to dominate over all other processes in the atom, and that is what is the business of making a laser, right? So what you do is, you create a situation with lots of electrons in the excited state. Take lots of atoms, put all of them, many of them on the top. So you see that, and this state is long-lived, metastable state. Almost, of course, you cannot have completely stable, almost stable, that is what we call as metastable state. And these electrons are simply waiting for a photon to stimulate. That's the condition you have to generate. So by the way, even though these mechanisms were known as early as 1905, Einstein's original paper, it took 55 years to understand how to make atoms run like engines. Put in energy, extract, put in energy, extract. It took 55 years. It's non-trivial. So invention of laser is not by chance. It is actually a slow, steady development of ideas. Only eventually we came to know how to run atoms like engines, thermodynamics of it, right? So the other thing that is important, so now some elements of it. So this is what happens to the active media. You need to do this. For the resonator, what you require is, you have heard of this, right? You give me two boundary conditions, only some solutions are allowed, right? So a number like oscillations in a string. You want this to be a node, this to be antinode. Only some wavelengths, periodicities are allowed, not all. That is what a laser cavity does. What it does is to basically make the transverse electric field go to 0, because it's a metal. And then once that happens, only a certain number of wavelengths are allowed, and that is what selects the frequency. So now you are able to, so you see that, so what people were doing wrong for 50 years was also that they're trying to make 3D cavities. Okay, so when you make a 3D cavity, one can think of it as various modes. All kinds of modes are allowed. Then people realize that if we do 3D cavity, it's a problem. Let us go to 1D cavity, one dimensional. 3D cavity is confinement in all directions. 1D cavity is there. By the way, this idea is what led to Nobel Prize. You would think, yeah, oh, I could have done it, yeah, but then people didn't do it. So Bashov and Prokhorov in Russia, and these guys in this thing, they went from 3D cavities. By the way, the maser was made of 3D cavity, but the laser is made always of one dimensional cavity, and because of that very reason, that you have fewer number of modes, and hence you can select them more carefully. Okay, and then just want to tell you something important, that if I change the reflectivity of my mirrors, right, the reflectivity can be 50%, like I look into the mirror in the morning. It can be 60%, 70%, 80%. So as you make the reflectivity higher, the wavelength allowed is narrower. Do you understand that? It becomes more and more narrow. So the narrowness or the monochromaticity of the light of the laser is not coming out of the atom or the simulated emission. It is coming out of the cavity, selecting a very narrow band wavelength. That is, so we require that the reflectivities of the mirrors is very, very high. Okay, so just like these are called modes, and one can also talk about transverse modes. So there is a distribution of light in the front, but so then one can ask, you know, are they stable? That is, if I put in light, will it bounce back and forth, or one day it will walk out, right? So we have to worry about stability. So there are these little things that I'm sure you will study as you go along, one depending on the curvature of the mirror and their relative distance and the refractive index, if you like, all this. So some little bit of equation, but basic idea is this, that I will get gain in my laser, which is proportional to something called absorption cross section, if you want to just cross section, scattering cross section, okay, multiplied by the number of electrons in the excited state minus number of electrons in the ground state. So usually what happens is, in the ground state electrons are more, so you see that N2 minus N1 is always negative. Okay, if gain is negative, implies there is only absorption. Only when you make N2 larger than N1, that you can start having gain, which is a positive number, and that is what you require to make a laser, right? So just give me another 5-10 minutes, and I will. So one can do, I know this is actually the Ruby laser description. So what you have here may not be visible. So you have the ground state for the Ruby. Ruby is basically chromium atoms which are doped in some Al2O3. So that's a Ruby. It gives you, reddish glow. It gives reddish glow because you absorb everything in green and blue. Green and blue light is absorbed, so red is what is left and looks red. So what you do is you put in this light in green and blue, higher frequencies. These guys decay into a metastable state and they remain there. And then you put this inside a cavity which has got the right frequency selection at this frequency, and then it will start lasing, right? Similarly, so what you want this number here N2 to become larger than N1. This is one way. It's not so efficient because you are fighting against the common ground state. Ground state is always occupied with lots of guys. So people made better lasers by looking at something called a 4-level system. So this is the excited state that you want, metastable state. The ground state itself is leaky. So what happens? You keep removing stuff from here. This is almost empty. So whatever you put in here starts lasing, right? Because N2 minus N1, you want that to be positive. If N1 is almost equal to 0, your job is done, and that is what a ND-YAG laser is. Neodymium atoms which are put in a crystal of yttrium aluminum garnet, and one can get lasing. So, and then the other beast which is there is this gain is not free, in the sense that you say you create a lot of guys in the stimulated emission, so a lot of light you create, generate lot, get out more. More you put, more you get. It's not like that. What happens is the more you put, more light is there in the medium, more stimulated emission. That means it will bring down the electrons faster, implies less gain. So as you build in more light, your gain is actually decreasing. So there can be no situation where the light is going to run away. It happens only in Hollywood movies that the laser has gone crazy and it is killing everybody. Laser is basically trying to shut down at every event. The more light you produce, lesser the gain. So gain actually goes inversely with the amount of light which is there. The greater the intensity, smaller is the gain. So the maximum gain you get when there is very little light coming out. That's the strange thing about lasers. So a runaway laser is simply not possible, right? So wherever you have gain or laser light, that gain will actually start decreasing, and this is what is called as gain saturation. So anyway, I don't have the time for going through it all, but then one can come up with very simple understanding, but there are other issues related with it. So the problem is this, that laser, the line width, the width of this, okay, it is, what you want is very narrow. We want narrow beam of light in terms of frequency. But then what happens, there is the fact that there is spontaneous emission which you cannot stop. There are all kinds of, if it's a gas laser, there is a pressure which is there. If it's a solid state laser, there are phonons which are there. All of these lead to broadening of this line. Okay, so the broadening comes with a price. So if I have something which is narrow band like that, when it becomes broadband, it not only decreases on the top, it also widens up here. So a lot of energy goes into the wrong set of modes. This is something which is intrinsically there. You want to make this better and better, so you want to understand broadening mechanisms and help them. Not just that, for example, neodymium ND-YAG laser, your neodymium atoms which are sitting in various points in a lattice, some of them have got a different neighborhood than the other guys. Everything is not identical. So moment he sees a different world around it, their energy levels are changed differently because the local electric and magnetic fields are different. So you see that even though I put in neodymium atoms identically everywhere, they themselves don't behave identically. They have their own resonances which are slightly shifted, leading to something called broadening. So what you see is a combination of all these different atoms in different environment, giving you slightly different light and gives you a broad light. That is what is broadening mechanism. So anyway, so the whole idea is this: you have some kind of a gain, and you have these cavities of the laser. There is something called a threshold above which losses just beat it. So the places where gain is below the threshold, you will not get lasing. When the gain is above the threshold, you will get lasing. And because it's a one-dimensional cavity, you have only 5 or 6 of them, and you can pick up one to lace. That is simply not possible if I had a 3-dimensional cavity. This would be a million, and picking up one wavelength will not be possible. That is why they got the Nobel Prize. So okay, so it's basically a combination of cavity as well as atoms put together that gives you narrow band light for lasing. And no, we don't have to talk about time dependence, but let me just tell you this idea. And so now what you want to, you've got a continuous light, but you want to get it in time. You want to time variation of it. So you can do this exercise yourself. Take a sine wave, okay, and take two sine waves with slightly different frequencies, if you like, okay, or even phases for that matter. Add them up, you will get something like this. Take 3 of them, you get something like this. Take 4 of them, you will get something like this. As you add the number of sine waves, you will, with some phase relationship, you can't randomly add sine waves with random phases. You start getting narrower and narrower pulses. So this is similarly the same thing. When the phases are locked, you get narrow pulse. When phases are random, you get something like this. Okay? So now what do you want to do? We want to get a pulse of light, narrow pulse of light. You want this to be 10 to the power minus 15th of a second, femtosecond pulse. You want to get it of light. You need to put in all these broad frequencies, different frequencies, add them up together and maintain their phase relationship. Somehow create a phase relationship which is maintained. Otherwise, random phases will not give you femtosecond light. And this is what is done to produce a femtosecond laser. Pulse. Narrow pulse, which is extremely narrow, which is basically dependent on adding up various frequencies. You have heard of the beat phenomena. It's essentially more and more you add up, the narrower you would get in terms of beat, and that's what is the idea. So there is something called mode locking, and one can, I don't have the time to talk about it, but anyway, various things can be done. But let me just come to the summary of it. So you see, actually, merely amplification is not enough, right? Light comes here, amplifies, comes this side. No, I need to oscillate it. It has to go back. Only while going back, it is collecting more power, and also it is selecting a particular frequency. So it's actually light oscillation by stimulated emission of radiation. And for obvious reasons, people don't call it a loser, they still call it a laser, right? That's precisely the physics behind it, but then that's the reality, but then you're stuck with it. All right, so this is something that I have covered. I hope transient part I have not covered, but I have given you some flavor of it. I'll be happy to take any questions that you might have. Anything? You're too shocked, is it? I kept on speaking without taking a breath. So either nothing has gone in, and there are these advanced topics that we worry about using light. Okay, this is just, if you have any question, query, or anything to do with your labs or whatever, or you are very hungry, you can also tell me that, then we can break. Yes? Yes?
So pumping is used, right?
Yeah.
So what actually stands for pumping?
Yeah, so in the cases which I showed you, what we do is take a lamp. So for example, ruby laser, you have to give blue and green light. So what we do is take a lamp, which is like a halogen lamp, right? And then there's the active medium is just a crystal, which is like a tube, this small tube. And then you surround that with this light, which is basically like a tube light which is wound around, and then you run that light on. Once you turn that on, that light is absorbed by this. So in that, very many things have to be done. This, putting this light on itself is going to generate heat. I want to make sure that heat is less. I want to make sure that whatever I generate is the light precisely required to my active system. Putting light anywhere else is going to only heat up the system. So the choice of the wavelength and the kind of mechanisms. Other things people do is, imagine, take a something which is elliptical cavity, elliptical. So you put in one rod at one foci and the pumping rod at the other foci. Whatever light you put in here, it gets absorbed by this rod and so on. So many things are done to couple light into, or it may not be light, it can be also a gas discharge. Helium neon laser, there is a discharge. Electrons are exciting them. So different things are used. All right, so I'll leave you to hopefully a very nice lunch. Okay, thank you very much.